All right. So in this video, we'll be talking about the exponential smoothing method. We'll talk about exponential smoothing method that includes trend and seasonality together. We'll slowly build up to that. Now, one of the things that we have, why the exponential smoothing method is considered slightly more useful sometimes than, say, the multiplicative decomposition method that we did in the last video, is that the multiplicative decomposition method is more of a static method, while the exponential smoothing method, if you get more data, you can incorporate it better into the method. You don't have to redo the whole thing again, as opposed to multiplicative decomposition, where the whole level and trend and everything will change once you incorporate more data into it. So it's not as future data friendly as the method that we're going to talk about in this video, right? So simple exponential smoothing method does not consider trend or seasonality, and it's only useful when demand is essentially level. In this case, demand is not. We know that this is the data for the data that we use in multiplicative decomposition here. This is the Tahoe salt data right here. So we know that it has trend and seasonality, but let's see how it works. So to do this, for multiplicative decomposition, we need a number called alpha. Right? So alpha tells us approximately what. So the way we are going to do this exponential smoothing is that, because we are assuming that because exponential smoothing is only useful when demand is essentially level, we are assuming that we know approximately what the level is, and every time period all we are doing is we are changing the level just a little bit by taking into account the error that we had in the data. We are saying that, well, we have error. Part of the error component is from the systematic systematic forecast component, and the other is just the random component. Right? The random component, we can't do anything, but part of the error might belong to the systematic component. So the question is, how much of that error do we incorporate into our current data? And to do that, we use the number alpha. So if we say 10%, that's how much we are going to incorporate. All right. So let's see how that is done. So once you have demand, so the first thing that we need to do is to do any of these exponential smoothing methods. So to calculate the forecast, first thing that we need to do is to calculate the average. Right? Let's calculate the average demand. Right? Will be average of all the demand values. Right? And this is going to be the forecast for the first time period. That's the average. So that's your forecast for the first time period. All right, so you'll see that here. It's the average demand of the all time period. So that's the forecast for the first time period. And then in the future, we'll calculate the forecast as we can revise the forecast by taking part of the demand and part of the level. Right, so that's essentially what we are going to calculate. Okay. So future forecast, you're saying, is going to be, well, the 10% times the actual demand, right, plus 1 minus 10% times the level, and level is essentially your previous forecast. Previous forecast, right there. All right. So that's your forecast. So again, it's 10%. So this, I'm going to make an absolute reference. So what does this mean? This means that 10% is the actual demand and 90% is the forecast. The reason for that is we are saying that the forecast is essentially what we had from before, and that's okay, right? Forecast plus forecast error, right? It is alpha times demand plus 1 minus alpha times the forecast. Yeah, that's the idea. So 90% of it is the forecast, 10% of it is the demand, and that's what you have. And there you go. And that's what you see. And obviously notice that the forecast and the demand are really far apart. If you, let's say, if you want to calculate the MAD, so you can calculate error, you can calculate absolute value of error, and you can calculate MAD, right? So error is the difference between the forecast minus the actual demand, or the other way around. And this will be the absolute value of error. Finally, MAD, which is the average of the absolute errors. I start at the top point and always end. And that's the error, MAD. So the MAD is 9,276, which is way more than the 1,587 that was there with multiplicative decomposition. The reason for that is we are not accounting for either the trend or the seasonal variations, right? And that's why the forecast is the forecast. So yeah, let's calculate exponential smoothing with trend. I'm just going to call it the name. So it's called the Holtz model. So this is where we are incorporating trend into the data, right? So what we'll do is we will take this data right here. Then we'll have a level. Okay. Final forecast. All right. So we have level and trend, right? Now we need some, we need to figure out what level and trend are. So there are a couple of ways of figuring out what level and trend are. So when you're using the Holtz method, how do you calculate level and how do you calculate trend, right? So to do that, you can you can obtain the estimate for level and trend by running a linear regression analysis, right? So how do I do that? So I have my demand numbers and I have my period numbers, right? So I can calculate level and trend this way. I'm going to call this L0 and T0, right? L0 for that. So I'm going to calculate. So level, remember, level is the y-intercept. So it's going to be intercept of the demand numbers and the time periods. And T0 is the trend. So that's the slope. Slope of all the demand numbers and the time periods, right? So slope and that, so I have my numbers. So level, initial level is going to be level and trend is going to be trend, right? So once I have that, I calculate my forecast as just the sum of my level and trend, right? That's my forecast. Straightforward. You can calculate error and do some error analysis, but we'll do that later. All right. So now, so this was for the first time period. So let's calculate the level and trend for the next time period. So to calculate the level for the next time period, we need that alpha, but we are also going to require a beta, which we're going to use to calculate the trend, right? So on top of the alpha, so let's say alpha and beta. So we need two smoothing constants. Let's keep it at 10%, and let's say this makes us 20%, right? Okay, so how do I calculate level? So if you notice the formula for level, the formula for level is pretty straightforward. It is alpha times the demand plus 1 minus alpha times the forecast that we have, which is just level plus trend, right? Hang on. So this is going to be alpha, which is 10%. I'm just going to say, okay, fine, you know what, alpha times the current demand plus 1 minus alpha times the previous forecast, right? So this is the current demand, this is the forecast, is exactly what we're doing in the previous example, and that's what we're going to do here. That's my level. Now as far as trend is concerned, trend, the formula is a beta times the difference in levels plus 1 minus beta times the current trend, right? So it will be plus beta times the difference between the trends, right? Difference between the levels plus 1 minus beta right? So 1 minus beta times the previous trend. Okay, my forecast is just level plus trend. There you go. So these are my formulas here. I can just copy them down here, and I can go down one extra step, if I remember correctly. Oh no. Okay, apparently not. Right? Okay, so these are my forecasts for the future time period. Now you notice that these are all essentially continuously increasing. So this captures trend but does not capture seasonality, right? So error and error analysis, let me just wait a second, what the hell? Right. Let me make sure I had the formula right here. Yeah. Okay. All right. Right. So that's the Holtz model. You notice the Holtz model has a higher MAD than the basic exponential smoothing method, and that's fine. Means that just capturing trend without seasonality is more destructive than just not capturing anything. All right. Oh, oops, sorry. I think that was the mistake, right? Forecast minus demand. Maybe it will be better. Yeah, slightly better actually. Okay. 9,276, but 8,037, it's not that much better. So, but still Holt's method is better. And finally, we'll talk about the Winters method. Winters method is where you include both trend and seasonality into the data. So let's see how that works out. Now, for the Winters method to work, you have to first do multiplicative decomposition because we need these seasonal indices that we calculated. We calculated the 4 seasonal indices. We will need that for the Winters method, right? So Holt's method, so let's just okay. Right. So the level and trend also comes from the multiplicative decomposition method. So level and trend are here. So let's use that for Winters method. So level will be equal to this level. Trend will be equal to this trend. And seasonal index, I'm just going to copy it. Right. So I got seasonal index. Just gonna place the values. So I have my first set of seasonal indices. So I have that, then I can get forecast, which is level plus trend times the seasonal index, right? 1001, 9117. It's definitely closer. I guess this is the closest because this will also be 9117 exactly. Yeah, that's right. Okay, now we have to update level and trend. So the way level and trend are updated is essentially the same. Even in the Winters method, we will do something similar. Now for the Winters method, unlike the previous two methods, we not only need alpha and beta to update the level and trend, we also need gamma to update the seasonal index. So let's say alpha is 0.1. Oops, why do I? Beta is 0.2. Let's say gamma is 0.25. Now, in these cases, is alpha of 0.1 better than alpha of 0.2 or alpha of 0.3? It's just a trial and error method. You're going to have to figure it out. I'm just using 10%, 20%, 25% because it sort of makes sense to me, but there really is no real reason why you would use one number over the other. Sometimes there are industry standards, sometimes some numbers have worked out for you, so lots of different reasons why something like that might happen. All right. So let's update the level. So when you're looking at level, so the way you update the level is you take alpha times the deseasonalized data essentially plus 1 minus alpha times forecast, the level plus trend that you have. So let's calculate that. So this is going to be alpha times alpha. Oops. So it was demand divided by seasonal index, right? Plus 1 minus alpha times level plus trend from the previous time period. Level plus trend. All right. 1 second. Right. Let's calculate trend and seasonal index in the same way. So let's begin with trend first. So for trend, it was beta times right. So it was beta times the difference between the previous levels plus 1 minus beta times. Right. It's 1 minus beta times just the trend for the previous time period. There you go. And that's my current trend. Then I can get my forecast. So I got the level and trend for the first set of indices. So now, so far I have not messed with the seasonal index. So let's see what happens when you increase the seasonal index. So I'm just going to copy this all the way down. Some of these are going to be divided by zeros, right? Because we wrote the formulas of, oops, what is this? Divided by that, right? Wait, am I missing some formula? No, seasonal index. I already said seasonal index. So let's do seasonal index. So when you do seasonal index, you'll notice that we will use gamma, right? Times. Now you'll notice that to calculate the seasonal index, you always take the data from the previous occurrence of the same season. So you do demand divided by the level times gamma plus 1 minus gamma times the previous seasonal index, right? Right. Demand divided by the level Plus 1 minus gamma times the seasonal index. Times the previous seasonal index, right? So it's demand divided by, to calculate level, it's demand. So it calculates season, it's demand divided by the level, right? Level. Okay, done. All right. And then I can calculate the forecast. Okay. Yeah. Okay. That's it. So that's the forecast with the trend and seasonal index, and that's what you have there. Right? So once you have that, you can calculate error. Okay, there you have it. So that's the mean absolute deviation for this method here. All right, and that's it. And that's the Winters method. So we did the exponential smoothing, basic exponential smoothing method. We did the Holtz method, and we also did the Winters method. Right? But remember that to get the initial estimates for the Winters method, you'll have to run the decomposition method to get that data. And that's pretty much it. So this video is already again very long, so I'm going to stop right here. There's one more. No, this is it. This is the last video. So we talked about two different methods of forecasting. We talked about doing it with regression analysis. Then we talked about doing it with exponential smoothing. Exponential smoothing just by itself, then Holtz and Winters model. We also talked about the measuring forecast error and whatnot, right? So this is where I'm going to end the forecasting portion of this topic. So predictive analytics are very important in supply chain management, and their main impact is when doing demand forecasting. Now they are useful in other things also. For example, they can be useful in pricing and whatnot. But then again, I'm going to end this video here. I already have enough videos for this week. So you can talk about predictive analytics in supply chain management later on. After this class, so starting next week, we'll be looking at prescriptive analytics for supply chain management. We'll look at many different prescriptive analytics methods, but we'll begin all of that in the next week. For the time being, I'm going to end this here, and I'm going to post all of this online. See you all, in the next video. Take care.